Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is Module 2, where we talk about the axioms of probability and the concept or idea of conditional probability. So the axioms of probability, you can think of them as some fundamental rules about probability that we're going to use kind of as building blocks to do more interesting things, maybe. The first two axioms, I think, are relatively obvious for people with any background in probability. All the first one says is that any probability value has to be greater than or equal to 0. So there's no such thing as negative probability. The second axiom says that the probability of the universal set occurring has got to be equal to 1. And this follows just from the definition of the universal set. So we've said that the universal set, or the sample space for a random experiment, has to contain all possible outcomes. And so the probability of one of the outcomes in the universal set occurring always has to be equal to 1. So again, kind of an obvious thing, but actually we're going to be using this second axiom a little bit later on to help us with some probability calculations. Finally, the third axiom is perhaps a little bit more interesting. If we have two mutually exclusive events, that means two sets that have no elements in common, then the probability of A or B occurring, the union, which again we associate with the word or, the probability of A or B occurring is equal to the probability of A happening by itself plus the probability of B happening by itself. And this is a really useful relationship, because we can see how this could be used in kind of a verbal probability problem. If we have, from some kind of relative frequency experiment, if we have the probability of A occurring and B occurring, we don't have to do another experiment to determine the probability of A or B occurring. We can just add their two probabilities. Now, I should say that this third axiom is one of the most abused things in probability by students. I see third axiom mistakes lots on exams and on assignments. You can only add probabilities if the two events are mutually exclusive. This requirement is key. What does it mean for two probability events to be mutually exclusive? It means they cannot happen at the same time. So I see lots of students, just adding probabilities kind of at will almost. And if you end up adding, as we're going to see in the next slide, if you end up adding probabilities for events that are not mutually exclusive, you end up with a value that's too big. And in fact, if you're working through an exam problem or an assignment problem, and you find all of a sudden that you've got a probability value that's greater than 1, which is in violation of the second axiom, probably what you've done is you've added probabilities for events that were not necessarily mutually exclusive. And so what happens if we have two events that are not mutually exclusive? Does it mean we can't use the third axiom? Not quite. We can still use the third axiom for non-mutually exclusive events, but as we're going to see in the next slide, we have to modify it a little bit. Okay, so what happens if we're dealing with events that are not mutually exclusive? They share one or more elements, and we still want to determine the probability of their union, right? It turns out that we can do this. We just have to modify the third axiom a little bit, and as we modify it, we get to learn a little bit of, maybe come to a slightly deeper understanding of what the third axiom is all about. So what happens if the intersection of A and B is not equal to the null set? Well, let's start with a Venn diagram. Here we have a set A. I'm trying to be close here. And another set B. Okay. And the elements that they share are here, A and B. So we know that we can only apply the third axiom to sets that do not intersect. But we can define the union of A and B in terms of sets that do not intersect. So A union B is equal to the union of A, and everything in B that is not in A, which is given by this region here. B is also equal to the region I just shaded, everything in B that is not in A, and everything in B that is in A. So this region here. Okay? So this is just kind of, I guess, manipulations, right? But the key thing to note is that these two sets and these two sets are mutually exclusive. They do not share any elements in common. So that means we can use the third axiom for both of these expressions. So the probability of A union B is equal to the probability of A plus the probability of all the elements in B that are not in A, which is just a straightforward or straight across application of that expression. The probability of B is equal to the probability of all the elements that A and B share, plus the probability of all the elements in B that are not in A, which is an application of this expression here. So we're using the third axiom, and it's interesting, like in particular, this second expression is not a union expression at all, and yet we're still using the third axiom. And so what we can do is we note that this element and this element are in common, so we just manipulate these two expressions algebraically and solve for A union B. This little V thing is a typo here, it shouldn't be there. But when we combine these two equations, we get this expression. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection between those two sets. So you can think of this final expression as kind of a modified third axiom, right? So we've got the first two terms, probability of A plus the probability of B, is just the third axiom, just like we had on the previous slide. But when we've got this third term, which we can think of as kind of a compensation factor. Okay, so if we draw a Venn diagram, because my top one is now very messy, this is set A, this is set B. So now we want to determine the union of A and B, but we know that the union operator does not double count elements that they have in common, right? And we saw that in our very first example where we had two sets that contained the number 3. But when we took the union, the number 3 occurred only once in the union. So if we have two sets A and B that intersect, and we just add their probabilities and do nothing else, what happens is that we end up double counting the region where those two sets intersect. And so this third term, subtracting off the probability of the elements that A and B have in common, basically just compensates for that double counting. So it's kind of a, it's subtracting off this region in common to make sure that we only count it once towards our expression. One thing also that's kind of interesting is that we know, since probability values always have to be positive, that this generalized third axiom indicates that the probability of A union B is always less than or equal to the probability of A plus the probability of B. And so that means a couple of things. One thing that this leads to is something called a union bound. So if we add probabilities together that may or may not be mutually exclusive, we know that we've achieved an upper bound for that probability. If they are not mutually exclusive, then the actual probability value is going to be lower. But there are cases, particularly sometimes in communications when we're trying to derive a probability of bit error, where we use the union bound just to make our math a little bit easier. And having an upper bound is not such a bad thing because it's a conservative. If we're working with upper bounds, we're being, conservative in the case of probability of bit error. It also shows that, again, though, like the caution I had on the previous slide, if you find that your probabilities are too high, or if you find that your probabilities are perhaps greater than 1, it's probably because you've added two probabilities together that were not mutually exclusive. The next concept that I want to talk to you guys about is that of conditional probability. And conditional probability is an extremely important idea, particularly for engineers. So the whole reason why we study probability in the first place is because often we have to deal with random systems that have uncertainty built into them. And so we've got this, this toolbox, I guess, of probability techniques that we can use to deal with uncertainty. But that doesn't mean we like it. Engineers, I think, fundamentally do not like uncertainty. We want to be 100% certain. And a lot of what we do when dealing with random systems is to try and reduce our uncertainty, or to increase our confidence level in how the system is going to behave. And the idea of conditional probability is very central to that. So conditional probability basically allows us to take information about the system and use it to reduce our uncertainty about the different outcomes that we can expect. This information is sometimes called side information, particularly in sort of the estimation and communication fields. And so we'll go through some basic examples of conditional probability, and I'll hopefully illustrate what I mean by this. So we can start off with just the basic definition for conditional probability. The probability of event A, given that event M has occurred, is written like this. So the probability of A, and then we've got a vertical bar M, and it's calculated as the probability of the events A and M occurring at the same time. So the probability of the intersection of A and M, and divided by the probability of just event M occurring by itself. So again, the practical meaning of this is that we've got two possible random outcomes. A and M are both, fundamentally random. However, somehow we've been able to observe M. So M has occurred. And so now we have this information. We have a little bit of information about our system. And so conditional probability allows us to determine whether or not the information that we have about M will, in fact, affect our uncertainty level about whether or not A is going to occur. And so we're still dealing in very kind of, just abstract terms here. I'll come to an example in a second that will illustrate this in perhaps a more clear way. Before we get there, though, let's consider a situation where A is a subset of M, right? So we have M and A. That means that the probability of the intersection of A and M is just equal to the probability of A, right? Because the intersection of M and A is just equal to A, because all the elements that they have in common are within A. And so the probability of A occurring, given that we know that, that M has occurred, is equal to the probability of A divided by the probability of M, which is always greater than or equal to the probability of A, because M has to be less than 1. What this means is that now that we know M has occurred, the chance of A occurring has increased. So our uncertainty has in fact gone down. How is this possible? Well, it becomes more clear if I draw the universal set. Okay, so without any information about M, we have to assume that any outcome in S is possible. But once we know that M has occurred, basically we've now narrowed down our options. we know that all of the outcomes outside of M cannot possibly occur. So in fact, we've reduced our uncertainty. Now, we haven't completely eliminated it because A is again within M, and there are some elements in M that don't correspond to A. So we do have some uncertainty still within M, but we've narrowed things down. And so what happens then is that the probability of A, given that M has occurred, is greater than or equal to just the plain old probability of A before we had any information about M at all. And so that's the basic mechanism, the fundamental mechanism. So this side information that we have has somehow ruled out some outcomes and has increased our certainty or reduced our uncertainty. So let's illustrate this with an example. So let's consider our good old six-sided dice, and let's let the random event M be even, so rolling an even number, and the random event A correspond to rolling a 4. And so the intersection of A and M is just equal to 4, because M contains 2, 4, and 6. So we know that the probability of A and M, which is just equal to the probability of 4, is equal to 1 over 6. We also know that the probability of M is equal to 3 over 6 by the classical definition of probability, which is just equal to 1/2. And so the probability of A, given that we know M, is equal to 1 over 6 divided by 1 over 2, which is equal to 1 over 3. So what's happened here? Well, basically what I'm describing is a situation where, let's say the six-sided dice is hidden under a cup. And so I sort of jiggle it around under the cup. And then without looking at the dice, I say, what's the probability that we've rolled a 4? And you say, well, it's 1 over 6, right? Because all the results are equally likely. Then what I do is I peek under the cup and I say, I'm going to give you a hint. I'm going to give you a bit of information. I'm going to let you know that the number that I have rolled is an even number. Now, what's the probability that you've rolled a 4? Well, you can do this conditional probability calculation, or you can just reason it out a different way and say, okay, well, you know, there used to be 6 possible outcomes, but now there's only 3 possible outcomes. I know for sure because now we know that the number is even. I know for sure that 1, 3, and 5 are not possible. And so 2, 4, and 6 are the only possible outcomes now. They're still all equally likely, and so the probability of 4 is just equal to 1 over 3, because our universal set is essentially shrunk, which was what I was illustrating with the Venn diagram on the previous slide. Now, we can, I guess, have another example, which is probably a bit trivial, but it still kind of continues the point, I suppose. What happens if A and M look like this, where M is a subset of A? Then the probability of A given M is equal to the probability of AM over the probability of M, which is equal to, in this case, the probability of M over the probability of M, which is equal to 1. Now, what am I talking about here? Well, again, same experiment. We roll a six-sided dice under a cup, and I look under the cup and I say, I've rolled a 3. And then I ask you, what's the probability that I've rolled an odd number? And you can say, well, 3 is an odd number, and I know it's a 3, so the probability that you've rolled an odd number is in fact 1. And so that's what we're talking about here. So that's a trivial example, but it is important to note kind of what's going on here with this extra information, with this side information. We're reducing the uncertainty that we have in our system, which is extremely important for engineers, and we try to apply this idea over and over and over again. Okay, so I mentioned that a very important part of this class is taking kind of verbal or real world problem descriptions and translating it into probability mathematics. And so what I want to do is in this kind of for the remainder of this module, we'll talk about a few more new ideas, but I want to work through at least two, fairly detailed examples to give you an idea of how we can use set theory and the axioms and a verbal problem description and kind of combine them all together to solve a problem. So the first problem we're considering is an integrated circuit testing proposal, and this is kind of based on the idea that in modern times integrated circuits are created on large sort of circular sort of flat pieces of silicon called wafers, and the fabrication process deposits layers of metal and silicon onto the top of these wafers, and then the wafer is literally chopped into kind of square pieces afterwards, and the little chips are then put into packages and sold to be used by consumers. And so these chips are incredibly complicated, and testing is a very big problem. I mean, how do we test them sufficiently so that we're sure that they work, but at the same time, we don't want to spend so much time testing that we never get a product to market. And so there's always this kind of balance we're trying to strike between providing good, reliable products to the customer, but not spending a lot of time and money on testing, or at least trying to minimize the time and money that we spend on testing. And so this problem that I'm going to talk to you about is a very simplified version of this larger real-world problem where we have a wafer with just two integrated circuits on the wafer. Circuit number one, or integrated circuit number one, and IC number two. And so just as for our notation, let G1 represent the situation where integrated circuit number one is good, it has no defects, and G2 represent the situation where the second integrated circuit has no defects. And so using a relative frequency approach, what your company has done over time is sort of look at the results of testing these two integrated circuits. So traditionally, you have tested both integrated circuits, and over time, you've accumulated logs on the test results, and using relative frequency, you've come up with 4 probabilities. So the probability of both of the chips being good is equal to 97%. 97% of the time, both chips are fine. 1% of the time, the first chip is okay and the second chip is bad. 1% of the time, the first chip is bad and the second chip is okay. And 1% of the time, both chips are bad. Note that what we've got here is a universal set, right? So we've represented all possible outcomes of these two chips being good or bad. And so that means that if we, another thing that we can observe or state about this is that these 4 events are mutually exclusive. So if both chips are good, then one of them can't be bad. If one chip is good and bad, then they both can't be bad or they both can't be good. And so all 4 of these outcomes are mutually exclusive, which means that we can add their probabilities together by the third axiom. And if we add all of these probabilities together, we'll find that the result is equal to 1, which has to be true if this is going to be a universal set, which is what the second axiom tells us. So already we've been able to, even just in kind of the description of this problem, apply some of the concepts of the axioms of probability. So we've got a valid universal set. The outcomes in our universal set are mutually exclusive. We add those probabilities together and we get 1. Now, what I want to talk about in this problem is a proposal that someone has come up with in your company to save money. And the proposal is, rather than always testing both chips, let's just always test the first chip and then only test the second chip if the first chip is bad. This is based on the idea that if something goes bad with a chip, it's kind of because the whole wafer is bad. You know, something's maybe spluttered across the wafer, or there was some problem with the alignment of the wafer. And so the idea is that if the first chip is good, chances are the second chip is going to be good as well, because we've got a good wafer. And if the first chip is bad, chances are the second chip is also going to be bad because, you know, maybe we've got a bad wafer. And so this idea will reduce the amount of money we spend on testing. We only test the second chip if the first one is bad. However, there's some risk here, right? Because if the first chip is bad, or if the first chip is good, we're sending out the second chip without testing. And so we want to sort of evaluate our risk. And so we want to calculate the, first of all, does this scheme improve the probability that our testers are going to find a problem? So if the first chip is bad, is it really more likely that the second chip is going to be bad? That's one of the things that we can ask ourselves. The other really important thing is, what's the probability that an untested bad chip gets sent out to the customer, shipped out to a customer? And so these are kind of real world concerns that any kind of manager would have at this proposal, and we're going to use the tools that we've learned in this class so far to solve those questions. Okay, the first question we're trying to ask or answer is this a better use of resources? And the way I'm going to answer that is to calculate the probability of a tester finding a bad chip if we test every single IC number 2, and then calculate the probability that a tester finds a bad chip if we only test the second IC after the first IC has been shown to be bad. And so if we're testing every single integrated circuit, the probability that the tester finds a bad IC number 2 is just equal to this. Now, we don't have this probability in our problem description on the previous slide. And so you might say, well, I guess what we could do is just again do a relative frequency experiment where we just look at chip number 2 and then, you know, do a bunch of testing and observe what happens over time. We can definitely do that, but it's not necessary. In this case, it would be a waste of money because we have the information we need in order to calculate the probability of the second chip being bad. We can see this if we draw a Venn diagram. So here's our universal set. Here's the situation where G1 is bad. Here's the situation where G2 is bad. Now, what we have on the previous slide is the probability that both of the chips are bad, which is this region here. And we also have the probability that G2 is bad and G1 is good. And so that's the intersection of G2 being bad and then all the area outside of G1 being bad. And so that gives us this region here. These two sets are mutually exclusive. They don't intersect, so we can add their probabilities. We can use the third axiom. And we have these two probability values. They're both equal to 1%. So then when we add them together, we get an overall probability of 2%. That means that 2% of the time, if our testers are testing every single IC number 2, they're going to find a problem. Okay, so they're finding all the problems, but 98% of the time, our testers are testing good chips. And so maybe we could direct them in a slightly better, more efficient, or send them in a more efficient direction. And so that's what we're going to try and figure out with the second part. So what if we test chip 2 only if chip 1 is bad? let's say this another way. Given that we know chip 1 is bad because we've already tested it, what's the probability that chip 2 is going to be bad? This is the kind of language that suggests a conditional probability calculation. So if you ever see the words, given that something has happened, what's the probability of something else happening? That is a conditional probability problem. Or I could say, if we know that chip 1 is bad, what's the probability that chip 2 is bad? Again, we've established something that's normally random. We've established that it's a certainty. And so then we're asking about how it affects another probability. So that also suggests a conditional probability calculation. So what we're really trying to figure out is, if we know for sure that G1 is bad, what's the probability that G2 is also bad? It's equal to the probability that they're both bad, just by the definition of conditional probability, divided by the probability that G1 is bad. This top probability we have directly from the previous slide. This probability we can determine using exactly the same method that we did up here. And so then we get 1% divided by 2%. This is a typo. It's not 0.05, it's 0.5. So if we test chip 2 only if we know that chip 1 is bad, 50% of the time now we're going to find a problem with chip 2. So it turns out that there is indeed a relationship between the failures of the two chips. And now we're directing our testing resources in a much more efficient way. Our testers are finding problems half the time, where before they were only finding problems 2% of the time. So far this seems like it's a good idea. The second, so based on the previous slide, it looks like we are now making a more efficient use of tester resources. However, the other really important question we need to answer is, what's the probability that under this new testing regime we ship IC number 2 and it's actually bad and we haven't tested it? So we know that we only test chip 2 now if chip 1 is bad. So if chip 1 is good, what's the probability that chip 2 is bad and we ship it to a customer? Note my language there. So let's kind of play with that sentence a little bit and sort of rephrase it. If we know that chip 1 is good, what's the probability that chip 2 is still bad, right? Because that's the probability that it's going to get sent to a customer without being tested. Or we could say, given that we know chip 1 is good, what's the probability that chip 2 is still bad? All of these sentences suggest that we need to use a conditional probability calculation. So normally the random event of chip 1 being good or bad, normally the event of chip 1 being good or bad is random. However, in my sentence I'm saying, given that we know for sure that chip 1 is good, what is the probability that chip 2 is still bad? And so that's this conditional probability calculation here. And then just using the definition for conditional probability, it's equal to the probability of chip 1 being good and chip 2 being bad, divided by the probability that chip 1 is good. Now, we can figure out the probability that chip 1 is good using the method that we used on the previous slide to calculate the probability that chip 1 is bad. However, I'm going to use a slightly different approach that exercises a few more of the ideas that we've learned about. So what I'm going to do is I'm going to define a new universal set, and it's going to be a smaller universal set. And the elements in the universal set are going to be chip 1 is good and chip 1 is bad, right? Those are the two elements in our universal set. And that defines all possible outcomes as far as chip 1 is concerned, right? So we're not worrying at all about chip 2 now. We know that these two outcomes are mutually exclusive. Chip 1 and chip 2 can't be good and bad at the same time. So by the third axiom, we can add their probabilities together. We also know that if this is a universal set, the sum of all these probabilities has to equal to 1. And so using the second and the third axiom together, we can write probability of of chip 1 being good plus the probability of chip 1 being bad is equal to 1. Or in other words, since we know the probability of chip 1 being bad, the probability of chip 1 being good is just 1 minus the probability of chip 1 being bad. Now, this is a little bit trivial. Probably this agrees with your intuition in most cases, but it is important to kind of deconstruct it a little bit, point out specifically what probability ideas we're using here when we write this fairly simple fairly simple equation, because later on in other problems, we're going to be redefining universal sets in, maybe not quite such a trivial way. So anyway, using this approach, we can figure out that the conditional probability we're after is equal to 1% divided by 1 minus 2%, which is equal to 1.02%. So that means 98.98% of the IC number 2 that we send are okay, and 1.02% of them that go out to the public are bad. Is this good enough? For a real chip manufacturer, it would not be good enough. This is this defect rate is much too high. Most manufacturing, particularly electronic manufacturing outfits, talk about 5 nines quality, and by that they mean 99.99999, like 5 nines, percent quality. So 99.99999% of the things that they're selling to consumers are fine. The reason why they need such a high confidence in their product is because, particularly in consumer electronics, you sell millions of these things per day. So even a 1% failure rate can add up to a lot of money. So building on our understanding of conditional probability and also partitions, there is a concept called the total probability theorem that basically just adds another kind of equation or a relationship to our toolbox for solving probability problems. And so let's assume that the sets A1 through AN are a partition of the universal set S, some universal set. So the probability of some event B is equal to the probability of B conditioned on all of these sets in the partition multiplied by the probability of each of these sets within the partition, and sort of all added up. The proof of this is that the event B, or the set B, is equal to the intersection of the universal set and B, right? Because B is a subset of the universal set by definition. We know that S can be defined by its partition, so we replace S by its partition, which is the union of the sets A1 through AN. And based on the distributive property of intersection and union, we can then write this as the intersection of A1 with B, the intersection of A2 with B, and so on. Now, all of these terms are mutually exclusive because A1 and A2 by definition don't intersect because they're a partition. And so that means we can use the third axiom to say that the probability of B is equal to the probability of the intersection of A1 with B plus the probability of the intersection of A2 with B, all the way up to AN. And then just using the definition for conditional probability, we know that probability of B given A is equal to the probability of AB over the probability of A. So just solving for this numerator allows us to write the total probability theorem in terms of this. And so I'm just going to leave it here for now, but then in the next problem that we do, we're gonna make use of this relationship. So building on the total probability theorem, we can now talk about something called Bayes' theorem, which is a super important theorem, again, for engineering applications. And I'm just going to kind of open the door a little bit here, truly sort of applying this theorem and understanding it kind of leads to the area of statistical signal processing, which is a whole another graduate course. But we can at least talk a little bit about some of the concepts related to Bayes' theorem, and then we'll go on to do an example. So we can build up Bayes' theorem by noting that the probability of A intersection B is equal to the probability of B intersection A, because it doesn't matter which order you take the intersection with. And using the definition of conditional probability, this means that the probability of A given B times the probability of B is equal to the probability of B given A times the probability of A, which again seems fairly obvious, but let's manipulate it a little bit further and then solve for the probability of A given B, which is just equal to this expression. And then let's use the total probability theorem on the denominator, where we define a universal set that consists of the event A occurring and A not occurring. So A and not A. So why is this of engineering importance? Well, often engineers are presented with systems where we want to determine an input, and let's call this A. And we want to basically figure out whether A has occurred or A has not occurred. What's an example of this? Communication systems are great examples of this. So A corresponds to a 1, not A corresponds to a 0. And so we want to figure out whether a 0 or a 1 has been transmitted. So it's kind of a hypothesis testing sort of situation. But we don't have access to a direct observation of the input of the system. All we have is the output B. And there's some randomness inside this system, so that if we transmit A, we're going to get outcomes that, vary randomly. And so what can we do? Well, one approach that we can take to dealing with this system is to try and guess which input we received based on our observable B. And one approach is something called maximum a posteriori detection, or MAP detection. And so we assume, or we choose the outcome, A or not A, that maximizes this conditional probability. So which has the bigger conditional probability? Based on the fact that we've observed some value for B, we've sampled some noisy receiver and we've got a certain voltage value, and that's B. Given that we've observed B, what's more likely? A or not A? And then we choose whichever one of these outcomes has the largest conditional probability value. Or we would call these the a posteriori probability values, because they're the probability values after we have observed B. And so how does the Bayes theorem help us with this? Well, it gives us an expression here that will allow us to calculate the a posteriori probability, in this case for the event A. So here we have the probability of A, the probability of A, and the probability of not A. These are what are known as a priori probabilities. So these are the probabilities of A and not A occurring before we observe B. That's why they're called a priori. And generally we know these perhaps from some description of the problem. We know that A is perhaps a little bit more likely than B, or than not A. And if we have those values, we can plug those into this formula. You'll note that we also need conditional probability values that are the probability of B given A and the probability of B given not A. These are what are known as likelihood functions or likelihood probabilities. And they're basically, they basically give you the probability of observing a particular B given that we know that either A has been transmitted or not A has been transmitted, or the input is A or the input is not A. How could we possibly get these probability values? Well, we assume that we have access to this system, right? It's a communication system that we have in the lab before we deploy it out in the field, and we can do experiments on it. And so one experiment we can do is to force the input to our system to be equal to A, and then observe the probability that we observe a particular B at the output. So this would give us the conditional probability here. We can then do an experiment where we fix the input to be not A, observe B, and then using some relative frequency experiment, we can get this value. So by doing kind of design experiments on our system, we can get these two probabilities, and we can use those in our a posteriori Bayes theorem equation when we want to calculate the actual map probabilities during system operation. Now, I'm really kind of glossing over a lot of details here. As I said, to really understand map detection and likelihood functions, you do need to take a course in communications or statistical signal processing. I just kind of wanted to introduce it a little bit here. We're going to use Bayes' theorem in this next example, kind of almost as an equation of convenience. We're not really going to talk about map detection necessarily, but I just wanted to sort of introduce these terms at this point because they are of great engineering importance. Okay, so it's time for another example. Now, this example is kind of a biomedical kind of example that deals with creating a machine that tests for disease. Now, we have some information about this disease. You're testing for a disease D, so we use D to represent the disease, and it occurs in 0.5% of the population. If the disease is present, your test alerts the medical staff 97% of the time. Okay, so that seems to be pretty good, right? I mean, if you guys got 97% on the exam in this class, you would feel pretty good about that. The machine, however, also gives a false positive 1% of the time. Again, just hearing that number, it's like, okay, well, that's not bad. If I make mistakes 1% of the time, I'm usually not too hard on myself for doing that. But the question that I want to ask is, if your machine gives an alert or an alarm, what's the probability that the person actually has the disease? And this is actually a pretty important question, right? Because if the machine gives an alarm or it indicates that you've got this disease, all kinds of serious stuff happens afterwards. Maybe this person needs surgery. Maybe they have to get more testing. At the very least, they've been frightened, right? Because you've said, well, this doesn't look too good. And if they end up being healthy after all, at the very least, you've scared them for no reason. And so this is a very important question that kind of goes to the heart of testing for a disease. And we see this, frequently, like for example, when a new strain of influenza comes out, it seems like it takes an incredibly long time just to develop a test to determine whether or not the disease is actually present. And this example is going to kind of illustrate why it takes, why that time is required. So let's look again at the language of our problem description and see if we can put it in terms of probability. So we know the disease D occurs in 0.5% of the population. Let's write this by saying the probability of the disease is equal to 0.005. If the disease is present, your test alerts the medical staff 97% of the time. Note the language there. So normally, whether or not the disease is present is a random event. The occurrence of the disease is random. But if we know for certain the disease is present, then the test alerts medical staff 97% of the time. Given that we know the disease is present, the test alerts medical staff 97% of the time. This is a conditional probability that we've been given. And if I use the letter A to represent an alert or an alarm from the machine, the probability of an alert, given that the disease is present, is equal to 0.97. The machine also gives a false positive 1% of the time. What does a false positive mean? It means that there's no disease there, but it gives an alarm anyway. We would write this as an alarm if there's no disease being equal to 0.01. Now, this is the information that we have, and we're going to have to try and manipulate this information in order to answer our question. So the question has asked us, if your machine gives an alert, what's the probability the person actually has the disease? Given that we've received an alert, what's the probability the person has a disease? This is a conditional probability we've been asked to find. What's the probability that we have the disease given that our machine has given an alert? Using our just the definition for conditional probability, this is equal to the probability of the disease and the alert occurring at the same time divided by the probability of an alert. So if you look at the information we had on the previous slide, we don't have any of this information at all. So rather than just kind of giving up, let's manipulate this equation to see if we can get it in terms of something that we actually have. So using the total probability theorem, we can express our numerator as the probability of an alarm, given that we have the disease, times the probability of the disease, which we have, right? We have both of those pieces of information. And using the total probability theorem on the denominator, we can write the probability that we have an alarm, given the disease, times the probability of the disease, plus the probability of the alarm given that we don't have the disease, times the probability of not having the disease. Right? So our universal set that we've used on the denominator consists of having the disease and not having the disease. And so we have all of these values. We don't have the probability of not having the disease, but we know that it's equal to 1 minus the probability that we do have the disease. And so we can now plug in all of our values. 0.97, 0.005, 0.97, 0.005 plus 0.01, 1 minus 0.005 equal to 0.33. So the probability that we have the disease, given that our machine has set off an alarm, is only equal to 33%. So our machine, when the red light goes off on the machine, we're sending people to the hospital, and only 1/3 of those people actually have the disease that we're testing for. So what went wrong? Basically, the problem is our detection rate and our false alarm rate. In particular, our false alarm rate. We're sending people to the hospital that don't have the disease because of false alarms. A 1% false alarm rate seems like it's fairly low, But the problem is the occurrence of the disease, the probability the disease occurs is even lower. Only 0.005% of people coming into our office actually has the disease. And so this false alarm rate is high relative to that, which means we're sending a lot of people into the hospital that don't necessarily have to be there. So this highlights one of the problems or the challenges that we have when we test for disease, right? Which is why it takes such a long time to produce disease tests. Now, what are some ways that we could possibly improve this situation? Well, we could, in a fairly straightforward way, reduce the size of our universal set. Right now, I've said that the disease occurs in 0.005% of the entire population. Well, let's reduce that universal set a little bit. Let's say there's certain symptoms for the disease. For example, everybody with the disease has a red rash. Okay, so if we only send people into our testing machine that have a red rash, all of a sudden the occurrence of the disease in that population is going to be quite a bit higher than 0.005%. And so if the occurrence of the disease starts to increase relative to our false alarm rate, we may actually still get acceptable performance out of this machine, even without modifying it. But this calculation, I hope, will sort of illustrate some of the things that we have to deal with when we're doing that kind of biomedical type design. The last concept I want to talk about in this module is the concept of independence. And this is a really important idea that's going to come up over and over and over again throughout this course. We can define two events. There is a sort of a strict mathematical definition for independence. Two events A and B are independent if and only if the probability of both of the events happening at the same time, or the probability of their intersection, is equal to the probability of event A happening by itself, or sorry, just the individual probability of A happening multiplied by the probability of B happening. Two events that satisfy this equation are considered independent. Conceptually, what independence means is, the occurrence of one random event has no influence over a second random event. So if A and B are independent, they don't affect each other. So A could happen, A could not happen, and it doesn't change or affect the probability that B will or will not occur. I find often that the concept of independence and mutual exclusivity are confused by students. So, and I think where this is coming from is sort of the Venn diagram drawing of mutually exclusive events. So let's say A and B are mutually exclusive. If we were to draw a Venn diagram, that means that A and B do not intersect at all. They have no elements in common. And so this kind of picture suggests that it's like, yeah, A and B are separate. They don't influence each other. They're not touching. However, mutually exclusive events cannot be independent. Remember what mutual exclusivity means. It means that the two events cannot happen at the same time. So if A occurs, we know for sure that B cannot occur, right? So clearly those two events are coupled, right? Whether or not one happens has a huge influence over whether or not the second event happens. And that kind of connection means that those two events cannot be independent. There is, we can illustrate the concept of independence using through conditional probability. The probability of A, given that B has happened, is equal to the probability of A and B occurring at the same time divided by the probability of B. That's just our standard definition for conditional probability. However, if the two events are independent, then the probability of their intersection is equal to just the probability of A multiplied by the probability of B. But these two events will cancel, right? Or these two probability values cancel, which just leaves us with the probability of A. So the probability of A, given that B has occurred, is just equal to the probability of A. A and B are independent. The fact that B has occurred has no influence at all over whether or not A is going to occur, and so we would expect this result. if we have a whole bunch of independent events, the equation for independence just extends itself. So the probability of the intersection of n independent events is just equal to the product of their individual probabilities. To conclude our discussion of independence and to conclude this module, I'd like to do a quick example. Now, most of the time, independence is a very intuitive thing, right? Remember, two things are independent if they are not at all connected, if they have no influence over each other. However, sometimes things they seem to influence each other, but they still satisfy the definition for independence. So let's consider a random experiment where we're rolling two six-sided dice, and let's define two events. A corresponds to rolling a 3 on the first dice, and B corresponds to the event where both dice happen to add to 7. Now, on the face of it, it seems as though these two events should, on the face of it, it seems that these two events are connected, because whether or not both dice add to 7 is obviously influenced by whether or not we roll a 3 on our first dice. But let's look at our individual probabilities. So first of all, the probability of A is just equal to 1 over 6, right? Because there's one outcome out of 6 on the first dice that corresponds to a 3. The probability of B ends up being 6 over 36. So there's 36 possible outcomes, 36 pairs of numbers from the two-sided dice. And as I've drawn here, there are 6 of those outcomes that correspond to adding to 7. And so the probability of B also happens to turn out to 1 over 6. Now, there is only one event that satisfies both A and B. So when we take their intersection, the only element they have in common is this. So the probability of the intersection of A and B is equal to 1 over 36, which is equal to the probability of A times the probability of B, which is 1 over 6 times 1 over 6. And so we would say that these two events are independent. Now, you can say, well, wait a minute, it doesn't seem like they should be independent, because if A occurs, we've reduced our universal set such that, the number of outcomes that satisfy B, some of them have been excluded, right? So if A occurs, we can no longer have this outcome, we can no longer have this outcome, and so on. So A occurring does indeed shrink our universal set, but it shrinks it to the point where, given that the probability of B, given that A has occurred, is still just equal to 1 over 6, because there's 6 possible outcomes and only one of them correspond to satisfying B. And so there is influence here, but it's influence in such a way that we still satisfy our independence equation.